make it work better tomorrow. So the first is Colin. When we looked at this from the program committee, because I'm on the program committee, we're intrigued by this idea of direct and relevant feedback, looking in particular at the issues flying around between content providers and last mile access providers, and trying to get a look into what was considered to be the private domain. My network, my data, my secrets. Not a good idea. How can we see inside folks' networks? So first speaker this morning, Colin Anderson, MLab. Thank you.
That was brilliant. So I should just set up. Cool. So I can't set up the conversation any better than that. As the internet drives economic and social development around the world, the telecommunications environment has a daily impact on the everyday lives of individuals. But these sorts of how the networks work, how they perform on a daily basis or under different conditions is opaque to users because of the complexity, but also because most of the data on this is highly proprietary and locked away. Worse yet, from a research standpoint, it's proprietary, it's under non-disclosure agreements, and it's not comparative, and it's not longitudinal. And so the ability to start to take networks and to compare networks against each other on a methodologically sound basis is scarce. This is what Measurement Lab is trying to combat. Or rather, this is what we're trying to start to provide data into the public domain to be able to allow for this sort of empirical cross-domain research. I very much liked part of the presentation that I think wasn't focused on enough yesterday when Dr. Lassner talked about what is modern research. Modern research is as much open as it is cross-disciplinary. So this is what Measurement Lab seeks to start to describe is what is modern research within the domain of network performance. And what we have is we have a global platform that is collaborative, that is open, and represents different sectors of what this question is. So with this partnership, we're able to start to do things like place measurement endpoints around the world for analysis of different aspects of network performance. So we have points of comparison on every continent that are geographically diverse, that are socioeconomically diverse, that are diverse in the network topology. And this is a network that is rapidly growing. So from that, we actually start to collect equally as diverse data. Basically, every country that you're interested in, we have some level of network performance data describing the conditions of regular users. So we've collected data on throughput. We collected data on network transparency. How do different applications perform across the network? Is there any sort of manipulation on the network? Is there anything that changes the performance? Along with that, we collect things like path information so that we can start to correlate the paths that are traversed by traffic with how this is influenced, how this has changed. What's really interesting about MLab, though, is that we have data from real users, and there are really three different ways of collecting network data. A user wants to know how its application or their connection works, so they open up an application or they open up a website, and a simple test is measured. This is sort of a self-selecting sample. It's interesting, but what's more interesting is actually that MLab has a number of cases in which we are integrated with with regular network applications. So these are applications that have a self-interest in knowing what conditions that they're behaving in because they want to auto-configure, because they want to select a different stream. And so because of this, we have sort of a non-self-selecting sample. We don't have people who are just have a broken internet or have a faster internet. We have ordinary users that are using internet applications, and we're getting speed measurements from this. And because this is a more diverse user base, we also have, this is how we start to have substantial geographic diversity in where we collect our tests from. The third, and to this more salient point, is that we also have partnerships with policy and regulatory agencies, because ultimately those entities have an interest in seeing the broadband deployment of their constituents. And so in collaboration with organizations like the Greek regulator, the Austrian regulator, we collect performance data in order to track, for example, what broadband deployment looks in different sections of the country. So across all of these, though, we have this substantial, large, and open comparative data set. Just because a measurement comes in from one client doesn't mean it's not comparable from another client. These are sort of standardizations of different sorts of tests. And so what we can do is, because we have this open sort of public domain commons of network performance information, we can collect measurements, we can collect them over time. We have over 5 years worth of data, over a petabyte's worth of data. We can take this data and we can start to slice it after the fact in ways that we might not necessarily have initially intended for. But because it exists, because it's open, because researchers, policymakers, and even network engineers looking at their own network are able to answer their own questions with this data, we can do things like looking at, for example, interconnection-related performance degradation that are useful for the public domain at a time. So if we take it, for example, the interconnection disputes in the United States that happened over the past couple of years, we have an interesting trend that this sort of manifests, which is a large number of individuals have certain sections of network data. This network data is incomparable across different network topologies. It's highly proprietary, and it's very rarely longitudinal. So data is scarce, and the only time that people release data on their network is when they're self-interested in. So it's stripped, it's incomparable, and it's proprietary. That's a nightmare from a policy-making process, or even just somebody who's interested in how their network fares against other networks. It's not a growth equation. So what we can do then, using Measurement Lab, is we have a tool. It's the Network Diagnostic tool. I'll explain simply what it is. You don't have to retain the acronym, but it's our most popular hosted tool. We get tens of thousands of measurements on a daily basis, every continent, highly representative. There are multiple different implementations. So we have the client integrations, we have regulatory partnerships, we have first-party clients, diversity of languages. So we have this large data set that's comparable and cross-domain. And all it is simply, for our purposes, is you take a connection, you try to push as much data down the wire as quickly as possible for about 10 seconds, and you start to look at how the network performance changes over that time. You look at things like latency, you look at things like bulk transfer, throughput, you look at things like loss. You get a lot of interesting variables out as a result of it, and what's important is that MLab retains all of this data. We have the Web 100 instrumentation. These are collected, they're made available in their raw form for anyone to look at after the fact. So because we have this going on a daily basis from all different endpoints or all different networks to different endpoints around the world, we can start to slice this data in an interesting way. So let's say that we have a situation in which we see that there is particular degradation for a user going to a particular transit provider. So what we can say is we can resample that. We can say, okay, for that access ISP, let's look at a different transit provider. Okay, that looks good. Normal performance, what you would expect. And I can show you a little bit more illustrative examples of how this changes, but we see it's okay. So let's try the same original transit provider from a different access ISP. That looks okay. So what we've just said is that probably what is not happening is there's probably not congestion within the access network. There's probably not congestion within the transit network. And so what's probably likely happening is that there's some sort of degradation happening because of the relationship with these two ISPs, the interconnection. So in the United States, we can apply this because fortunately we have a large enough sample size. We have tens of thousands of monthly samples from most of the major US ISPs. This isn't just the case for the United States, but for our example, we can take that first slice and we can say, okay, so there's been a lot of names thrown around about people who are affected by this, parties to this issue. So let's take a party that isn't involved with this. We have not seen InterNAP. We have an endpoint in InterNAP. So let's take all of the major access ISPs. Let's look at connectivity to InterNAP. By and large, it's stable. You know, you have sort of the spikes that occur because you're taking samples, but there's a consistent trend. So let's take an access ISP that hasn't been labeled, and let's apply it to a transit provider that has been sort of publicly called out. Stable. So it doesn't seem like it's the access ISPs themselves. It doesn't look like it's the transit providers themselves. So let's look at the access ISPs in question versus the transit ISPs in question. You see a massive change over time. And so these are the sorts of things that you can start to look at through this cross-section. Okay, so maybe that's one interconnection. Fortunately, MLab has different measurement points across the country within that same transit ISP and gets other access ISP samples. So let's look across the country. Same pattern. So if it's happening across the different ends of the United States, which is a very large domain, it's probably not a single source of technical failure. It starts to look like an issue that only can be caused by sort of what we call the layer 8 and layer 9 problems, the business disputes, the political disputes. And so we can continue to cut this in different ways. We can say, okay, we expect that within a well-provisioned network on a daily basis, we should not see, or on an hourly basis, a diurnal basis, we should not see significant change over the course of a day. We should expect that the network looks fairly consistent. If there's a bottleneck, if there's a lack of capacity, if users are all of a sudden trying to compete for a fixed resource and there is not enough resources, then we should see that basically as everyone goes home and consumes media content, browses the internet, goes to Facebook, that as they all compete to this, their share of this fixed resource should decline. They're competing with each other. So let's apply this to the cases in question. And what you see is substantial. You see that during the middle of the night is the only time in which people see the performance that they would expect. During the morning hours, the afternoon hours, and even worse during the evening when everyone is generally using their internet connection, it's nearly unusable over this transit network. That you are looking at basically half a megasecond of your capacity versus during the night, the median is about 20 megs. This isn't just download throughput, although these are inherently linked. Latency increases. So performance declines. And it's not just one transit provider. You start to see these sorts of trends across different transit providers. In this case, this is level 3 in Verizon. And you see this continuing. So it's not necessarily just linked with one content provider, or the deals that one content provider has. This is something that is happening in different relationships on an ongoing basis. So what we've been able to do is all of a sudden start to create this comparative data set that shows us network performance information across different service providers that we wouldn't necessarily have been able to do, let's say, if everyone was just releasing traffic graphs. We have comparable and open research. And so what this creates then is basically public interest data. In the case of the conversation that we were talking about, the regulatory conversation, MLab's data was cited just this year alone in 2015 by 14 different entities spanning all sides of the debate. So because we're also asserting that we're just trying to provide empirical results based off of real measurement. We're not necessarily a partisan organization. We are open for any entity that's interested in exploring this data. And so we become this neutral ground of asserting more material facts into a public debate. And this isn't just for lobbyists, but this is also incredibly useful for journalists that are trying to describe the problem to the public, because interconnection is a difficult thing as a general member of the public to understand when you think that the internet is just a cloud. So this is what MLab represents fundamentally, is a global public resource on network performance information. This is one, I just showed you one example of one use of one tool out of 16 out of a global data set of 100 plus sites across the world. But what this is ultimately they are measurements from your users, from real users. They're not self-selecting. They are happening in real time. And these are open, and they are comparative. And you have 5 years worth of data, and you will continue to have data that you know the methodology for the collection. All of the platform is open source. All of our methodology is open source. So your ability to go in and answer your questions about your network and compare your network against competitors' networks, against a baseline, is something that I think you can only do to this extent with the openness and the transparency of Measurement Lab. And ultimately, I think that what is important to us is that we are proven in this respect, and that we have this trusted neutral data set that can start to extend these conversations that previously had been sort of fought without real data. So ultimately, if you're interested in, this is something that's a public resource to you. There are things that you can do in order to further it, in order to have better data, such as hosting an MLab site. I can't stress that enough. But this is a public, common, global resource for everyone in the room. And this is the power that data can have on decision-making processes. All right. Questions now or questions later? Yeah.
Promoted by our technical people and industry bodies and so on, and I remember it was Java based.
Oh.
And then there was a security issue, and a bunch of browsers stopped supporting Java, and then NDT didn't work anymore. Has it been changed to a new technology, or will it be?
Yeah, actually, so one of the nice things about having an open implementation, which NDT ultimately is that you have different implementations of it in different language. Java is one that the maintainers have been interested in for the sake of being cross-platform, but actually NDT is largely C. And so what we've done since then is last year MLab released a Flash client, not preferable. We're working on a WebSocket client. And so ultimately, though, our intention is to have many different ways of getting to the same test, so that we can have these sorts of situations in which if you want to have a mobile application or a web application, you can run the same NDT test that is comparable across the board. MLab has, to us, I think ultimately we consider the Java basically deprecated for that exact same reason. So there are a lot of ways of using this on your network or for your clients, and mlab.net, measurementlab.net has a lot more information on what clients exist. And if anyone wants to get in touch with me as we release, for example, the WebSocket version, we'd be more than happy to let people know who are interested in that.
Any other questions? No. Really? Okay. Vesna and Cengiz, don't upgrade OS X right now, okay? Just leave it alone, because you're going to need your laptop. It's okay, we'll take the time out of morning tea. You right there?
Yep, I'm good.
Thank you.
Well, I thought I was good. Hi, can you hear me? Is this thing on? So I'm George Michaelson from APNIC Labs. APNIC Labs is a very small theatre company. We're kind of at the micro scale. The star of APNIC Labs is the chief scientist. He gets all the exciting roles and he gets the opportunity to go to the Oscars. I'm just the scientist in the background. So the thing with being a small research group, is that we have a really amazingly tight conversation. We're on the phone to each other every day and we're shouting. The rest of the work group in APNIC really don't feel very comfortable because I'm hurling abuse down the telephone at my co-researcher. He's in a more quiet environment and has the privacy of a room to hurl abuse back. But conversations are actually really important when you're doing research. The opportunity to talk to people about what you're doing and the opportunity to explore ideas is kind of what keeps it going. So some days you just feel like you need a conversation, and if you don't have one, you look for people to talk to and you wind up talking to yourself, and that's just sad. So we have this system for doing measurements, and it's based on Flash, and what we're doing is placing adverts worldwide, and we run sequences of pixel fetches that we control at the head to decide what gets done. And we're getting somewhere, it depends on the number of ads we run, but somewhere around 750 to 800,000 measurements worldwide per day on our current budget. We could actually scale this quite a lot higher if we decided to spend more money. And we're measuring qualities of things like IPv6 and DNSSEC and the behavior of the system that the end user has. We're performing a measurement using end user browsers. So we're exploring the behavior of the end users in the community and what they actually experience on their machines on the live network. Now, there's a quality to doing measurements that is kind of a bit of a life cycle. It's one of these wheel of life things that goes on in computing all the time. You start, you measure yourself. You don't find that very satisfactory, so you look at what you know and you measure that, and then you don't find that very good either. So you wind up measuring everything because it's the only way to find out what's worth measuring. And we did this. We started measuring ourselves. We measured our own website because it was easy. Logistically, we could get the data very quickly. That was actually a huge mistake because what we were measuring is the capability of you guys to come to our website from inside your core network. And it turns out you've all deployed v6 on your core network, it's just not on your customer network. So when we measure you, you all have v6. And we were getting these amazing worldwide v6 rates. Oh my God, the planet is on like 300% v6. This is phenomenal. But we were measuring your core network. It wasn't a real reflection of how the world works. So we did have massive overestimation of penetration. Okay, so we measured things we knew. We had some key relationships with people who were prepared to take placement of a JavaScript-based measurement. A gamer site in Australia and a general news and interest site in New Zealand took this. And that was really quite interesting. But then we started to notice that we were getting some quite odd skew. In particular, we managed to get placement on the site that Janet, the UK academic network, uses. I think it might be for pensions. So all those senior academics who are desperately finding out how much money they'll have when they leave the university system were our measurement source. And you know what? Academic networks have v6. So we were over-measuring v6 again, because we hadn't actually thought about the impact of targeting a specific site that has a specific repeat hit of users that come back again and again, and likely from the relationships we have to be high v6 sites. So we wind up in this place where the history of the wheel of life of measurement takes us to needing to measure everything. We had to find a way to get out there and measure the whole community. Okay, so the end game is measuring millions of things, and there's an obvious way to measure millions of things, and it would be nice to be in the position of being the agency that can measure millions of things, but we're not all there. So we wound up in this place where we decided we'd buy the measurements, and we looked to what technologies were out there that were cheap and effective to get people's eyeballs. How can you capture their eyeballs? Well, turns out that's buying ads. Now, the world of advertising is fascinating because the main aim of the game is to extract money from consumers. So adverts are actually very efficiently designed to get people to spend money. And that means that the bidding mechanism for advertising is very efficiently designed to reward people who spend money. You want to show as few ads as possible to get as many people to buy things. What we wanted was we didn't want to sell anything. We had nothing to sell. So we didn't want to bid for people to buy things. We wanted to bid for people to look at our ad and say, oh, I don't want anything from there, and then not click on it. So we actually had to work out how to use the bidding engine to say, can we just get impressions but not actually get clicks, which is the complete inversion of the bidding model. But we found a way to do this, which kind of depends on the thing that the channel agency you work with wants to take, in the end, our money. They want to be a good advertiser, they want to meet our goals, and for our budget, they wanted to maximize the presentations to make their daily budget. So they wind up showing our advert to as many people as possible, and their pledge is it's random. That's the whole name of the game. They don't show this ad to the same person a million times. That would be cheating. They show it to different people because that's what an honest advert broker does. So we get a large number of random placements worldwide of an advert that is very monotonic, grey, and doesn't invite people to click, which means we get heaps and heaps and heaps of impression. So at impressions, you get this question, what is the placement actually like? What's the uniqueness like? Well, we did some background work looking at placement, and we actually tracked the engine that's doing ad placement with an initial deployment, and then a subsequent day's deployment, and then a subsequent day's deployment. And you can see over this pattern of deployment that it's actually tuning its placement algorithm to try and even out the placement, because initially it soaked the ads, and then it thought, well, that's no good. I just showed like 1 million ads in 2 seconds. That's not helping anyone here. So it gently evened the flow out over the day. And eventually we arrived at a place where we actually had a really lovely even deployment. We actually fine-tuned this based on some information we got through Cisco, who used our version of modeling systems to construct their own advertising channel. And they demonstrated that if you ran a lot of ads in parallel, you got a more smooth behavior. And we wound up following that process and have now arrived at a much more even display rate that gives us a really nice view. So there's this quality that the time of day is influencing who gets presented to. And we've managed to make sure that we get a fairly even deployment over the day, which means we've avoided a lot of the distortions of placement because of it being exclusively in, say, 6 p.m. US time, which means we wouldn't pick up the qualities of internet behavior in Asia or in Africa or in Europe. We've got a much more even placement. But we still have this worry. We're kind of fringing on some of the developing economies. We've done well for the major economies. We're getting bulk placement. We're not necessarily getting the numbers we'd like on some of the more interesting emerging places. Okay, so the uniqueness question. If we actually look at our unique IPs and we do a plot of uniqueness as a cumulative graph, what do we see? Well, we compared our original JavaScript methodology, which is the purple line, with the placement rate of uniques coming from the flash mechanism, and it really is amazingly consistent. When you think about it, we're only sampling somewhere around 1 million things a day, and the global internet is now measured at 1.6 billion or some other large number. So it's really not hard for people to find unique new instances in a 30-day window that we haven't seen before. And that means that the sample size that we're taking, although it's quite large for our purposes, is really very small from the total population. We feel quite comfortable that we have a reliable long-term source of unique IPs. Okay, so success, mission achieved. Let's do lots of things. Let's plot it, let's graph it, let's tag it. Okay, let's drill down a bit and let's look at where we've got. So where are the IPs coming from that we're getting? So we do a table of the distribution of IPs and we sort by their volume. And this is our top 20 by volume for the economies. Okay, that's quite interesting. There are some quite interesting economies there. But there is a problem because there's another ranking, which is the ranking the ITU does for the number of users that are declared. Now, this is a annual measurement exercise where the ITU requests economies to submit information about their scale of deployment. And it's quite important to those economies. It's really something they feel strongly about. And these are good data. It is admittedly only an annual collection, but nonetheless, the population stats are coming from a reasonably unimpeachable source. And when we look at our comparison, we only got half of the top 20 in the ITU rankings appeared in our set. And more to the point, there was only one of them that we placed correctly by ranking position. So clearly, although we've got an amazing sample, we have a distortion issue in our count that we have to think about. So this skew, it really presented us with some questions, and we thought, what is a way that we can cover for this distinction between the eyeball count that we get and the actual economic ranking the ITU is collecting, which informs the relative weighting of internet users worldwide? We worked out a way to do a factor, an adjustment factor, based on the weighting that should exist based on the population rankings against the sample rates that we're actually seeing. So if we have this problem and we do the factor, that then poses this question: is anyone else doing a class of adjustment? Because we now regularly perform that adjustment in the stats that we present. And we do that for sub-regions as well as for the world. And we consistently appear to be recording 1 to 2% uptake rates lower than most of the other figures that people are publishing. And we don't think the other people are performing this class of bias adjustment. We think that they're actually showing unadjusted raw counts for the aggregate volume of V6 that they're seeing and plotting it, rather than taking account of the population dynamics. But the thing is, on an economy by economy basis, we actually have really quite good agreement with these measures. We've checked against Akamai, we've checked against the Google stats, and we perform quite well in the individual economies. It's only in the aggregates that we start to see this drift. This is our graph on the top, which is very noisy because of some aspects of the measurement process, compared with the Google graph on the bottom. And in crude sense, our trend lines are really very good. We actually do track each other for behavior, but we just have this consistent issue that we track 1 to 2% lower in overall value than Google does. Okay, so there's a second problem lying underneath this, and it's to do with the nature of the construction of the global default-free zone. There are people out there who deliberately construct networks using multiple ASN. Time Warner, for instance, they have 16 ASNs assigned. They have 12 that are visible in BGP if you go and look. We saw 9 of them. So if we look at this graph of Time Warner Roadrunner, these are the ones that we saw, and you can actually see that they have differential amounts of deployed V4 and V6. And by count, we have different weightings of the amount of samples we see from them on any given day. So this poses a problem for us in terms of how do we ascribe this particular ISP's weighting, because they're not presenting as a single ASN. And even if we aggregated everything together, we'd be ignoring the fact that some of their ASNs have not yet had a V6 deployment at scale because they're rolling out in staged regions, and some may never have a V6 deployment because they're not being used for customer-facing functions which require that. So there's not necessarily an answer, oh, bang all their ASs together and call them Time Warner. That may not actually reflect what's going on with that company. So we have a second problem, which is a collection. It's about 20 ASNs worldwide that appear to use a single ASN and have multi-economy span. So these are people who are providing fully international service. And we have a registration ASN that appears in our record keeping, the ASN of note. For instance, if we took Vodafone in Germany, they're in 3 distinct economies at volume. They're actually showing, 200 hits in the US, 3 in the EU, 13,000 in Germany. Well, they're predominantly a German ASN. I think we could feel comfortable saying that one, that's Germany. But if you look at Verizon, they have an enormous spread of economies they're deploying on. So if we make simplistic assumptions about registration economy of the ASN, we're going to misattribute by ASN count what's going on here. And we're thinking through how we want to account for these variances when we're weighting our measurements, because we think it's important we actually distinguish by AS number to help inform you guys about relative behavior of the companies. But where we know the AS is spanning multiple economies, we've got to think a little bit beyond the AS number into what's the distribution of economies that AS affects. So we do a data integration exercise where we map the resolver onto the experiment, and we have a unique code and time that we're doing. And we're using a number of resources to try and keep track of that. But there is this problem that we're now getting much more conscious of about the mapping to economy of the AS number and the region and the address. We're using our database, we're using MaxMind, we're using BGP for the origin AS. There are qualities around attribution of economy that we know are really not good. Now, the RIPE NCC have a research project that Emil Arben is running, which is to try and crowdsource better information on the location of address resources. This is a really interesting project, and it depends on participation of you guys to help provide quality information on the distribution of addresses. And there's information from facilities like Atlas, which can help improve on the location data. There's a research group, I think, in INRIA that have just published a paper in IMC using Atlas to do triangulation of resources. This is really good stuff. And I'd encourage you guys to think hard about the quality of data logging of address, disposition, and location, and to think about helping projects like the RIPE NCC crowdsourced geolocation information, because we all depend on this for the quality of what we're doing. So we have some other problems. We're really not good at measuring mobile devices because Flash, the primary vehicle we're using, is just not viable on those devices. Now recently, the ad channel we're using has started to do machine translation of Flash adverts into HTML5. And we were initially very hopeful that this was going to kind of carry us with them on the rising wave. But it turns out our Flash code is kind of strange, and it does not machine translate well. So we've actually invested time in writing HTML5-based ads modeled on our JavaScript that we originally wrote. And we are in the process of getting these approved for submission, which will improve that problem. We are also hoping eventually machine translation will work. And we have also explored other relationships to see if we can find other parties to work with to boost the number of ads we get from other channels. We think it might help improve the randomness long term. But although we can't actually cope with things like Flash not being visible, or more to the point, people blocking Flash, we have also realized that there are people who simply don't want to be measured. And one of the things we had to do in certifying with Google for our ads to be approved for continuing use is we had to implement the do not track flag. And we now fully respect people's statements in their browser client side that they prefer not to be tracked, and we terminate our measurement activity if we see that flag set. So we've become a lot more compliant with general practice. We can't directly measure people who block YouTube because the predominant channel that Google uses to soak adverts when it can't place actually is the YouTube channel. You may have seen when you watch YouTube videos, there's a bar at the bottom of the video that pops up. That's the space that we're mainly getting placement in. Our keywords are really quite good. The mechanism Google uses for advert placement is aimed at targeting ads. So our ads are targeted to cat, funny, video, car, and movie. And it seems that the world really is obsessed with new film releases and funny cat videos, and we're getting very good random numbers. But we may need to worry about skew to the little old lady bracket of cat fanatics. We may have to vary our diet a bit and include, rabbits or something else in there. The JavaScript measure we continue to do has a distortion of repeat visits. But the thing is, this kind of brackets to a low side consequence of an undercount, because there are things we can't measure in Flash, and a high side effect of Java oversampling. So we kind of have error bars placed either side of what we think is the real number. We feel like we're bracketing what's going on. So there's actually a lot of different qualities we can measure. There's a number of things to do with the dual stack system behavior, what happens in a v6 only world. We can look at RTT behavior. We've done a lot of work in DNS lately, particularly exploring the behavior of DNSSEC and DNS algorithms. But there is this question, what else could or should we be measuring? Now, this guy gets a bum rap. He gets a bum rap because of this statement he made, and everyone thinks he was just like off the planet when he said it. But I really, really like this statement. It might be kind of hokey, and it might be a bit like something Yogi Berra would have said, but I actually think it's true. If you don't know what are the questions out there, you don't know what are the questions to ask. So there's this, Rumsfeld moment, what should we be asking? And it's actually really interesting to ask you guys what you think would be interesting qualities of measurement. What would you like to know about the behavior of the network? I'm not saying we can do it, I don't know, but it would be interesting to understand what interested you to see if our technology is capable of measuring that quality. And we love talking with you one-on-one. If there are things you're interested in exploring, please come and talk to us and we'll see if our technique can help explore it. We have all our data available. We've actually recently adopted a much cleaner model. We had a kind of raunchy graphing mechanism. Jeff spent a lot of effort designing a really clean model that presents all of our data in a very consistent breakdown by world economy, by region, by structure that reflects the UN stats. And we're using some ideas Eric Vinke first showed for a graph that we've stolen quite freely with acknowledgements. And this is what we see happening out there in the world. This is America. This is the current state of Japan, which is really doing quite well. And we can do a drill down into each economy and get the AS ranking. So this is the ranking by V6 penetration. You can see that KDDI and Tuba are showing really phenomenal rates of penetration in Japan. But we can actually do a resort on this. We can take the sample count and we can then present this based on what we got by numbers. And if you do this, I'm not saying this absolutely is the relative ranking of market share, but I think for those of you in the Japanese community, this may be a fairly good model of the distribution of customer share by provider, at least in the top 5 or 10. Now, this is really very interesting to us because we have the ITU figures for the population and we have a random sample in an economy which we believe is giving us insights into the distribution by market share, and nobody else is publishing this. And we're doing it worldwide. So Jeff actually went out and constructed an estimated visible market share model, which we're now putting up for every economy. We're publishing regularly on a daily basis our sense of what we see of the distributed market share. And we're doing it for America. You'll notice that there's the problem for Time Warner, that because they distribute by ASN, they don't show as a single entity here. So there is some things here where it would be nice to group their ASNs and show what they do as a company. But again, that's actually a pretty interesting distribution of market share. I don't think it's 100%, but it's not bad. This is a small economy I'm quite fond of, and there's been some shifts recently at the top. There's also an observation here about data quality. You see that third entry for a company called Microplex? Microplex don't exist. That's Optus. That's the second-ranked telco in Australia that's actually Temasek Cable and Wireless. But because they inherited old records and have not bothered updating their WHOIS, we still record them as the original allocation. So we also do this for DNSSEC. You can get exactly the same form of data for the DNSSEC distribution. We feel quite good about this stuff now. We feel like our adjustment for skew is giving us a fairly good model of the behavior, and we think we have insights into market share that other people don't have, which we're interested in tracking long term. And we would like to invite you to look at our data. We're getting help from a bunch of people, the usual suspects, but more recently Comcast and Cloudflare as well. We do research, and it's fun.
As I said earlier, we are going to break into morning tea because they've got 2 more speakers and it's going to take a little longer than that. But I notice you're all extremely interested in this, so let's just roll on. If there are questions for George, I think just grab him anytime. He's here all week. And we'll move straight on to Cengiz from Packet Design. Thank you.
Thank you, Jeff. Good morning, everybody. I'm going to talk about network performance, route analytics, as well as SDN. So basically, about 10 years ago, we started to look at network performance. We studied jitter across 3 US and 1 European backbone providers. Actually, some of the folks that I have done the study with are here in the APNIC, in the APRICOT meeting this week. It was nice to see some of the old friends. But what we find out, actually, 99.99% of the time, that's 4 nines, that was very good week. Basically, during the week, we had more or less no jitter in the network, less than 1 millisecond jitter across the board. That makes it, as a researcher, someone trying to look at data, very boring. But that 0.01% of the time, it was actually extremely interesting to look at what was happening in the network. First of all, we don't have a laser pointer, do we? So first of all, the line on the top graph shows the packets, and then there is this 10-second gap where we actually have packet loss for 10 seconds. So we were sending continuous stream of 1 megabit per second traffic across US West Coast and East Coast, and for 10 seconds, none of those packets made it. And then followed by seconds jitter. So basically that's followed by all sorts of packets reception, and the jitter from 1 millisecond jumped to 7 seconds, 7,000 times. It was like huge. And then we reordered the packets. So what you see on the below graph is basically that line. So basically this line, it's not going to happen. Anyway, so that line basically matches the order of the packets that are sent, and then the y-axis is when they are received. If you look at it, basically the packets that are sent earlier, some of them arrive early, and then they go in time, and then the packets that are sent in the next round, it actually arrives later and so forth. Basically massive reordering. And when I look at this at the time, I thought this could be a routing loop unwinding. So basically, if you imagine a routing loop, as the packets go into the loop, they start turning. And during the 10 seconds when the network is converging, it actually drops those packets. But as it is turning, more packets come and they start turning, and it kind of all mixes it up. Eventually, when the routing converges, they come out at the other end, totally reordered with really high jitter. So that was our theory, and then we said to basically figure this out, to actually prove this theory, we needed to instrument routing. So what we did along with this measurement, we also started collecting ISAS packets in the network, and we analyzed this to figure out whether our theory was correct. Again, this is early 2000s. What we end up seeing is there were indeed excessive number of ISAS churn in the network. The top graph actually is the number of ISAS packets, link state packets, not label switch paths, ISAS link state packets per second. You can actually see there was a high churn in the network. Even if you remove the refresh packets that happens in ISAS, the blue graph gives you the changes that's happening in this network. This was an extremely dynamic environment with extremely large churn. And then we looked at remember, we have a measurement system in the East Coast and the West Coast. We looked at when does an LSP is seen in the East Coast versus when it is seen on the West Coast. And that's basically your propagation delay across the network. Remember, this is flooding. It's supposed to be it's supposed to be the fastest forms of communication. What we find out, actually, this is the propagation delay on the lowest graph, up to 2.5 minutes of propagation delay. So basically, a link fails, one end of the country sees it, and the other end sees it after 2.5 minutes. Which means anytime you do an SPF computation, your link state is not synchronized. As a result, you can really have long loops. This is actually going into the details. Basically, two routers think the network is different, and one say, hey, I must send my packets to Jeff, and Jeff says, no, that link is done. I need to send it to this other way. It sends it back to me. I send it to Jeff, and so forth. Basically, we have routing loops. And why do we have 10 seconds of routing loops? Actually, this is early 2000s, and routing convergence was really, really bad at the time. Vendors have a lot of issues and bugs and so forth. All of this has been cleaned up. So this is actually good news that we are not seeing this kind of convergence in the IP networks today. But what we realized in the process is looking at routing was essential to make sure that we are running the network in high performance. And some of these actually is coming back. So if you have a large TE database with auto bandwidth, you have more churn than those graphs. And hopefully there's some prioritization and so forth, so that very important link failures do not get delayed. So if you look at route analytics today, at the bottom we have collection. So you basically collect all sorts of routing data. You can collect BGP, IGPs, and flow data for traffic, RSPBT tunnels, multicast, whatever. That's your telemetry. Then on top of it, you write a whole bunch of analysis algorithms. You can see, for example, the root cause of BGP issues, what your exit routers is, and so forth. On top, you have your presentation level that may be reporting, alerting, and so forth. So, I mean, just to give an example from Jeff Houston's work, he's collecting BGP, and he's looking at to set models for that, how this growing, and so forth. And then he's making business decisions on the top level or forecast into the, what's going to happen in the BGP routing tables this year, next year, and so forth. And what does the industry needs to do about it? That, to me, is route analytics, basically. Using this routing, the big data, to do this kind of analysis. But you can do more stuff. You can do troubleshooting and visualization when there is problems happening in the network. And you can monitor a service or an application. And then when that particular application's path changes, for example, you can actually alert. You can assess the health of your network. Do you have asymmetric routes? Where do you have them? And so forth. And you can do topology-aware traffic analysis. All sorts of people do all sorts of analytics with this data, basically. And then the latest use case for it is used in the software-defined networking. I'm going to just show one of the use cases, and this is a very interesting use case. It's very operational. But before I go into this, can I see a show of hands? How many people have ever configured any routing protocol? Doesn't matter which one. Yeah, there's a few. And for the rest of you, if I lose you, please find me in the breaks. I'll be happy to explain it to you, what's going on here. But basically, this is the story that happened in one of our partner networks. And basically, there was a peering router, and it had a hot swappable line card, and they needed to hot swap that line card. And they pulled it out. Unfortunately, bugs and so forth, router crashed. So it wasn't quite hot swappable, basically. Router, as a result, crashed. This happens, it's not like the first time or the last time or so forth. But it had a very unexpected consequence. So when this network, this particular router was a major peering router. It was peering with another tier 1 service provider. Both of these happens to be tier 1 service providers. And you expect, because they peer in 6 locations, you expect when this router goes down, the traffic, first of all, the traffic that was exiting in the rest of the 5 locations to continue to so, as well as the traffic that was exiting here, it would be rerouted to one of these 5 other alternate places. But that's not what happened. What happened is entire traffic was black holed. And the outage lasted about 3 minutes. And this 3 minutes is too short for someone to accelerate. I mean, this case, basically somebody has to go to the NOC and then accelerate the case to the engineering level and then go to the router, try to figure this out. By that time, the problem is gone. But they had an ad revenue impact of 45 minutes because if you cannot do what you are doing for 3 minutes, you'll go do something else. And that wasn't actually quite a lot of damage for the service that they were running. So this is how the topology looked like. So I pulled the routers in the circles. These are the typical, they are 6 exit points to this other service provider. And then the way the graph is partitioned, these purple routers on the left are taking the purple that is circled, and then the green takes the green one, yellow takes yellow, and so forth. So basically, this is how the network exits to this particular here. And the one that failed is on the top right over there. So basically, that particular router on the upper right is the one that has failed. You can actually look at the activity in ISAS. There is these events on the right-hand side. If you look at it, basically, 2 neighbors of that failed router is telling, hey, this router has went down. One thing that you can build on top of this data, actually, you can build like a network DVR. You can rewind the time and look at these events, single-step them, and see their impact. As in that, what we did, what I did is basically, there are 4 events here, 2 of them failing it, and then within 3 minutes, they are coming up. 2 drop neighbor and followed by 2 add neighbor. As a matter of fact, it's not quite 3 minutes. You can actually look at the timestamps. I think the whole thing lasted 2 minutes and 24 seconds. But anyway, so what I did, I single-stepped these 2, and then looked at the exit points at this time. So we have our original exits that connect to the next service provider at the bottom, the blue ones. But in addition, we come up with 6 other exit locations in the network. What's bad about these 6 other exit locations that happen under these failures only is that these are core routers, and they have no eBGP sessions. They do not connect to any other network. They actually are, aggregating the edge routers traffic across the network. These are actually core routers. Why would this happen? Why would the network under failure think I should be sending my traffic to these other 6 routers instead of the true exits in the network? And to do that, what we did is basically find a path from one of the routers to a prefix that was exiting in that particular router that's going to fail. And that's the path before, and that's also in a table illustrated on the top. And afterwards, it can no longer go there because that router is down. You're expecting it to go to one of the other routers, but it's not going there. It actually ends up being stuck at that core router right before that exit. And if you look at the details, the path is following the same BGP route both before and after, but the BGP route needs to be resolved by an IGP route, and that is actually, in the case of the before, is an ISAS route that's to loop back for that exit router, whereas afterwards, the /19 BGP. So to understand that, here is a word on how does the route resolution work. So basically, BGP tells you, here are the destinations, here are the prefixes, and it has a bunch of attributes. One of these attributes is the next stop attribute. And this next stop attribute is an IP address. Basically, it says, hey, I am exit router Cengiz. Here are my prefixes. Set your next stop to me, to Cengiz, and then send the traffic to me. I'll know how to go to them. Basically, the IGP finds a path to Cengiz, and then I know which external destinations I need to send that so that it goes to YouTube and CNN and so forth. So there is this recursion in BGP route resolution. And then typically, for you to find a path to me, you must use your IGP. However, BGP is also allowed. So for example, you can have a BGP route whose next stop is resolved in BGP, whose next stop is now resolved in IGP. You can actually have multiple layers of recursion, and there are good use cases for that. And unfortunately, this is what happened here. So basically, before the failure, we had the ISS route resolving this particular service provider's prefix, and afterwards, it switched to a BGP route that says /19. This is why this has happened. But why? Why did this happen? Basically, where did this /19 prefix come from? So it came from because one other use of BGP is to announce your own BGP routes to the world outside. So this /19 is the address prefix range for this service provider. And it is in BGP because it is how it tells to the world, hey, if you must go to one of my customers, follow this /19 route. So everybody, all of you guys, service providers in the room, you have a route like this in your BGP routing tables. And this route is never intended to be used in this particular case, but it is in the routing table. So what happens is when the router crashes, IGP converges extremely fast. Within sub-seconds, basically IGP convergence. However, BGP takes 3 keep alive messages to converge. That is, in their time, usually, typically it's 30 seconds, but in their network it was a 1 minute keep alive timer. With 3 of them, it is 3 minutes. So it will take BGP to converge, it will take about 3 minutes. Within 3 minutes, actually, the router crashed and also rebooted. So BGP will never get a chance to actually reconverge in this case. But during this window, all of these BGP routes are in the system. Their next stop is no longer resolvable in the IGP because IGP has converged and says, hey, Cengiz is no longer in the network. Go use some other network. But the BGP routes are there, and the identity of Cengiz is in there, and there is this /19 that will resolve Cengiz as well because it is ultimately the least specific route that's actually going to find a path to me. But in this network, these /19s are injected by the core routers. Usually it is the case for all networks. And as a result, so all the traffic, including all the other locations in the network, not just the one that's going to me, the ones also going to Jeff and everybody will actually end up going to the core routers because when there are multiple routes, basically when we do route resolution, we pick the one that is closest. And the core routers are closer to all the other routers. So instead of sending it across East Coast to the West Coast, it's going to just send it to a core router, which will basically dump this traffic. What this illustrates is we are very good at designing networks when everything is up. When a router or a link or something fails in the network, the consequence of what's going to happen, nobody actually has designed them for. It's very hard to imagine all these protocol interactions and what will happen. So how do you fix this problem? Actually, the remedy is by V.J. Gill. He presented the remedy in NANOC quite a while ago. So basically, the way to avoid this, you must have your /19 in BGP. You cannot remove it, because if you remove it, nobody can get to you. So you must also inject it in your IGP. But you must inject it in your IGP at a very high metric so that it's never attractive. So, okay, Cengiz's /32 is gone. There is the /19 that tells, I also know how to go to Cengiz in ISIS, but it's so expensive that one of the other locations will be preferred over this route. Basically, you will poison the BGP route with a route in ISIS. And the root cause of this problem is because IGP converged much faster than BGP, but do not try to make BGP converge as fast as IGP. If you did that, actually, you really hose the network as well. But, so you cannot run BFT and make the BGP faster and so forth. That will actually create more harm than good. So I'm going to now switch subjects and then talk about the role of analytics in the SDN context. On the right-hand side, we have the typical architecture for a software-defined networking. At the bottom, we have physical and virtual routers, switches, as well as network functions, VNFs, NFVs, whatever. And then we have an SDN controller, which talks southbound protocols to these, and then northbound protocol to applications. And the premise of the SDN is that basically networks are now programmable. Instead of operators and so forth doing changes, one can write applications such as network overlays, which has been very successful in data centers, or for service providers, bandwidth reservations, and so forth on the top, and they can, by talking to the controller, can make changes into the network. But now the question is, how do we know these changes are good? What governs that these changes are okay to do? And to really understand that, let's look at how an application or a service is installed today in a network. For example, you may be a service provider and you may be signing up a major customer. And that major customer may have some SLA requirements from you, some bandwidth that is going to pass through your network. What do? You involve your planning group. And your planning group basically assesses the network and tells whether that particular customer, application, service, is actually, you're able to support that. If you need to change your metrics, or you need to set up some maybe TE tunnels, if the shortest paths are not good, and so forth, they design this thing. So if now the applications and services are being provisioned programmatically, then how do we do that? And for that, basically, you must use the analytics that you collected from the network and make these decisions. And to illustrate, let's look at one of the most talked applications these days in the SDN context, that is basically bandwidth scheduling application. What is this application? For example, let's say there is the Soccer World Cup in Brazil, and you happen to be, for example, let's say you want to watch this in Japan, and you want to basically send this uncompressed HD stream from Brazil to Japan, and you want to say, hey, the soccer game is at 8 o'clock, usually it's 90 minutes plus the 15 minutes breaks and so forth. For the next 2 hours, I want to reserve this much bandwidth. Find me bandwidth and then reserve it for me. And why is this application so attractive? Actually, if you look at how the networks are run today, there is actually a lot of abundance of spare bandwidth in the network. So Colin mentioned the Verizon and Level 3 debacle on the Netflix over-the-top issue. And they were writing these blog articles about how uncongested their networks were. So from those articles, we know that the Verizon average peak utilization is 46%. So there's actually 55% more capacity is available. And Level 3 also was running their network about 46 to 56% peak. So they still have half the network basically unused. So this is very attractive because there is this spare capacity. Can I make money out of this? Hey, maybe you are not going to let the over-the-top providers use it, Netflix or whatever, but maybe you will find a good way to, make money out of this. So it's extremely, basically, appealing. But there is a good reason why there is this spare bandwidth. But before we go to the good reason, let's look at a naive implementation of this. Most service providers will have link utilizations collected across the network. You know all the link utilizations in your network. You already have this, and you can actually use this to project, because the soccer game is not right now. You cannot use the current traffic utilization. It's going to be 9 o'clock tonight, but you can project what the traffic levels will be at 9 o'clock. This is not too hard. So you know the link utilizations at 9 p.m. tonight, and then you can say, hey, the path from Brazil to Tokyo is going to take this particular links, and then do I have this additional capacity? Since the network is around 45% of the utilization, you will say, yes, there is capacity. I can actually do a go or no-go decision based on that. And then you can use the SDN controller to set up this particular tunnel for you. In case the shortest paths are not available, it's possible that the bandwidth is not available on the shortest path, but you will find some constrained path that is actually going to be able to push you that. And then SDN controller will set that path. After 2 hours, it's going to remove it as well. I call that naive because it's missing why there is spare bandwidth in the network. And the number one reason why we have spare bandwidth in the network, as the link utilization goes up, delay shoots up. It actually has a knee around 65%. So basically, delay is acceptable up to or around 65 to 70%, and afterwards, it really shoots up. And when it shoots up, basically, that becomes really unbearable. That's basically, you are dropping a lot of packets, and even the packets that go through, they have really high delay. So this particular range is not that attractive. And the second reason is the network, especially the service provider networks, must accommodate failures. In very large networks, there's always one failed link at any given time. Actually, I'm hearing now from some of the global networks that they actually have 2 failed links at any given time. So basically, you are running a business, and then suddenly in the middle of it, a link fails, and you must reroute some of that traffic elsewhere, away from that link. You need to have this spare capacity. So which means basically to allow an application to say, hey, I can send your video from Brazil to Tokyo. You must actually see the impact, what's going to happen if there is a failure in that path or for that application or for other applications. And then the third reason that you have the spare bandwidth, to create new bandwidth requires, maybe someone even trenching and bringing a new fiber or turning on a Lambda or, talking to some other provider for a, dark fiber or something. It actually takes time. It's not something that, we can just do in software. It actually often involves, bringing physical resources, and that takes time. So you must have spare bandwidth so that when you need to upgrade, you have a time window of a couple of months or whatever it takes to actually bring that up. I can't help with the last one, but I can definitely help with the first 2. How do we tackle the increased delay? And first of all, instead of saying, hey, I want a go or no-go decision, instead of doing that at 100% link utilization, you can reduce it to 65 to 70% range, and then make your decision based on that. But in which case, you'll realize you don't really have abundance of spare capacity anymore. You cannot make that much money by selling this. And if you wanted to sell, all the way to 100% utilization, you must have bulk transfer. You must have bulk data. You must sell basically backups and so forth. You must sell services of that sort. Actually, Google gave a talk on one of the SDN conferences, and they were running the links at the 100%. Every service provider in the room is saying, oh, we are running at 50%. Why can't we do that? Well, Google can do that because all they are doing is index replication in this network, and index replication is bulk. So if it takes longer or slower or whatever, nothing is really hurt. Whereas as a service provider, if you were to do this, you will be hurting your customers instead of helping them. So this is not good for basically HD broadcast of video, or it's not even good for best effort internet surfing the web and so forth. But if you decide to do this, you need to make sure you actually are running differentiated services so that when the link utilization goes to 100%, your more valuable traffic is not impacted by that. And how do we, for the second one, how do we protect against the failures? That one actually you can do by simulations. You can actually fail every link and a router in the network and see the impact what's going to happen. But to know when a link fails where the traffic will go, link utilizations are not enough. Because link utilization says this link has 65%, you take that link down, where will that traffic go? Link utilization doesn't tell you where that traffic entered the network and where it is exiting the network. And luckily for us, the net flow data actually tells on that link, here are the flows on this link, And this is, the source address, this is the destination address. But source and the destination addresses can be multiple hops away. And then how can we map that? So basically, to do this computation, what you need is a traffic matrix, which basically tells you for every ingress router where the traffic is exiting. And then the flow data has the source and the destination of the addresses, but it doesn't really tell you where it's going to enter the network and where it's going to exit. It's going to tell it came from customer X and it's going to Facebook, which is multiple ASs away. But if you know routing, you can actually take that flow data and find its path. In this case, it's entering at this router here, router 15, and it's going to exit at the router 5 at the other end of the network, and it's going to go to Facebook and so forth. So basically, you know where it entered and where it exit because you knew routing, and from this, basically, you can construct a traffic matrix. You can construct ingress to egress traffic matrix. You can construct core router to core router one, or you can construct AS level traffic matrix that's also very useful for BGP peering analysis and other use cases and so forth. Once you know where the traffic enters and exits, and let's say you are going to simulate, if I can find my mouse cursor, once in a while it hides. Anyway, so if you can simulate the failure of the link above, and you can say, hey, what are the flows on this link? And you find each flow, and then you go to the ingress router and say, if this link was to fail, where would you send it? And it will tell you, I will send it over this yellow pad at the bottom. Then you can actually say, hey, under failures, when this link fails, what will be the new link utilizations in the network would be? And if you did this for every link, and if you wanted to protect against routers at every router, you would know whether you can actually run your network more hot. You can actually accept that HD stream and then guarantee that even under failures, you can actually carry it across the network. Well, to conclude, basically, analytics is extremely powerful, and it definitely impacts, routing definitely impacts the network performance. And if you have the root causes of these things, you can actually help run your network better. And with the SDN as well, if the controllers and orchestrators are making these intelligent decisions, they need to be analytics aware. They need to basically mine this data and find what's going to happen in the network under failures and so forth, so that they can actually do this task for us. Questions? Anyway, I am around if anybody wants to go over any of these examples, especially the BGP and GP recursion stuff, just find me. Thank you. Sure.
Now, we're going to run into morning tea, and that's just life. If you're desperately in need of tea and coffee, why don't you go and get it right now while Vesna sets up? You have exactly 1 minute. Otherwise, we'll take 25 minutes or so.
No, I'll do it in...
You don't have to. Whatever it's
Well, let's see.
this is one of the more interesting of the recent initiatives. We've talked about issues of trying to measure the network using existing infrastructure, but the other way of doing it is to actually seed the network with measurement boxes. And I think this kind of project is one of the more fascinating and interesting things that's happened in the last couple of years. Thank you, Vesna.
Good morning. My name is Vesna. I'm from RIPE NCC. I'm a community builder for measurement tools, and I'm not known for speaking quickly on this topic. I can go on for days, and now I'm standing between you and coffee, so I will try to do it fast. So my goal is to introduce the most recent developments with the RIPE Atlas and to invite Asian Pacific community to take part. So whether you are a network operator or a researcher or a programmer, these are the examples of how other people have already contributed to the RIPE Atlas and how the RIPE Atlas can help you. Just to kind of get a sense of who is in the room, how many of you have already used RIPE Atlas before? Wow, great. Great. So the introduction for the rest of you will be short, and then for those who have been using Atlas, I hope you will still learn something new today. The goal of RIPE Atlas is to do the active measurements globally of the internet infrastructure. We do that by deploying thousands of small hardware devices like this one with the help of volunteers who are hosting them in their homes, in their offices, so both with the eyeball networks and in the core networks. And these measurements are collected by the RIPE NCC and presented as open data available to the rest of the internet community. As of last week, we have more than 7,800 active probes in the network. And out of 20,000 users that ever visited RIPE Atlas, about 2,000 are coming back and are being active every month. What we do with these probes is 24/7 measurements towards root name servers. And those are so-called built-in measurements. If you are hosting one of these probes or if you are a member of the RIPE NCC, you get also a capability of doing the user-defined measurements to the destination of your choice from up to 500 probes at any measurement. And there is about 5,000 of these measurements being done by users every day. The measurement types that you can perform are ping, traceroute, DNS, SSL, and since last week also NTP measurements. And on the right-hand side, you see the top 10 countries with the number of probes deployed. So, as you can see, we are mostly focused on RIPE NCC service region, but United States are also very well covered. So that's why I'm here. We want to cover more in Asia and Pacific region. These are some of the photos provided by our users. So you can see the older type of the probe, the little black one, somewhere on the bridge in Amsterdam. And people, when they receive them, then they take snapshots and post them to us. And then on the right corner, you can see the RIPE Atlas Anchor. That's a different box that we have started deploying with the help of the community about 2 years ago, and then some of them also decorated by friendly ducks. So the RIPE Atlas anchors are larger boxes. That's a sucris that we are using there. And they serve at the same time as the more powerful probe and as a regional target. So once you put in one of those larger boxes in your network, we schedule the measurements towards it from about 200 probes and all the other anchors. So you get these so-called anchoring measurements that give you a regional view of the network around you. And there is, since I made these slides, another 2 anchors, so there is 111 already deployed, and there is about 1 per week being activated somewhere in the world. So if you're interested in hosting one of these, come talk to me later. I'm here the whole week. This is where they are located, and yeah, we have a lot of information about them also on our site. So if you are a network operator, you can use the RIPE Atlas mostly for monitoring, and this is one of the built-in measurements, or like several built-in measurements that we do for the root name servers, and this is the view of Japan. So all the probes are reporting which instance of the root name servers they are querying. We use it for monitoring the K-root performance, and if you go to the link on the RIPE Labs site, this article shows you like how did we deploy the data streaming functionality, and there is a little video which I didn't dare to show actually. I don't trust the live demos at these presentations, so you can see the video following this link. We also monitor all the other root name servers and about 30 ccTLDs and gTLDs, and that is the service called DNSMon. So this used to operate from our previous measurement platform called Test Traffic Measurements, and now these measurements are done from the anchors. For the regular users, you can monitor your network using the RIPE Atlas by utilizing the measurements, the ping measurements from multiple probes and using the Icinga plugin to generate alarms based on certain parameters that you set, for example, on the average measurements from, for example, 300 probes. If there is some discrepancy with the average, the alarm can be generated. Or if 10% of the probes go down, the alarm is generated. So the community of the operators contributed some examples for these plugins that you can just put in Icinga and you can get them from GitHub. This is one of the older measurement types that we have provided for the members of the RIPE NCC. So with your member login, you can go to RIPE Atlas and just schedule this one-time trace route from 1,000 probes that are capable of doing IPv6, and then you can get this visual impression of all the paths that actually succeed reaching your network, and you get another picture of all the paths that did not succeed. So this was very popular at the time of IPv6 day, when a lot of operators promised that they are going to deploy v6, and then they could see how much they succeeded. It's also possible to use RIPE Atlas for visualizing network outages. So on the very bad day when you have a network hiccup, at least you can console yourself with some pretty pictures that we produce with using RIPE Atlas. And operators also use it to see how are their users experiencing connectivity to their multiple sites, and then from this they can decide where do they want to improve the performance or where do they want to place their next site. So Wikimedia cooperated with us in producing this map. So that was a few examples about the operators, and there is some more in the additional slides at the back of my presentation. Now for the researchers, the newest feature are the NTP measurements, and currently there is no web interface for this, but I'm sure the API will be enough for people who want to find out the consequences of asymmetric routes or the very precisely measured network congestion. And the operators can also use it for choosing the best NTP server that they would like to configure for their network, for example. This is the OpenIP project that was already mentioned, and one of my colleagues is trying to crowdsource the geolocation of the infrastructure. So the RIPE Atlas is contributing here a lot of trace routes that we perform, and then on the map you can see which ones of them have a reliable geolocation and which ones are still missing. And if you are operating some of those networks, you can insert the more reliable information there, and in that way help the other researchers with more precise data. On this site you can find out how can you take part. And then here is Colin's paper that was using RIPE Atlas to show some disruptions that were happening last year in Turkey. There are also other researchers that are using RIPE Atlas for DNSSEC validation. I'm going very quickly through this because I would also like to get some tea. And then there is more and more research topics that RIPE Atlas is being used for. A lot of them are presented at RIPE meetings, and when people inform us that they have wrote a new research paper, we put those links on RIPE Labs. So on the RIPE Labs you can find a lot of user stories. And the code is also available on GitHub. So if you have something to contribute, please let me know. I'm administrator of the RIPE Atlas community repository, and the RIPE NCC staff is also publishing a lot of analysis tools, and we also put them on GitHub. So you can modify them, you can improve on them. It's all open source and free software. So part of our measurement code is also available, so you can see for yourself what our measurement methodology is. And again, this is one of the maps that can be useful for you. Excuse me, please reuse it, and if you improve on this code, upload it back to GitHub so that other people can benefit from it too. So this was how the actual RIPE Atlas measurement data can be used, and we also use a lot of help from the community to distribute these probes. So if you are a frequent flyer and you like the project, we can ship multiple of these probes to you, and then you can bring them to your friends. We will call you a RIPE Atlas ambassador, and we provide a web interface for you where you can register who did you give the probe to, and where you can chase those people who forget to plug in their probe, and that will be a great help. So, yeah. Come to me later if you want multiple probes. I don't have them here, but we'll ship them to you. I only have a few more to give to the individuals. We have also used some of the visualization software to compare the probe density with the population density so that the ambassadors can know where are the locations where we would like to see more probes. So you can see in Asia and Pacific region how well is the coverage of probes compared to people. And then we also accept monetary contribution. We call that sponsors. So if you have some money to spare and you like our project and you would like to use the data for your operations or for the research, please help us out. If you give us money, we will buy more of these probes, and we are going to promote your company in our slide material and on our website. Also, if you want multiple probes to deploy in your network, you can also sponsor us. We prefer the topological diversity. So if you just apply through the regular channels for the second and fifth and 10th probe for the same AS number, we might not actually ship it to you. But if you're interested in deploying a lot of probes in your network, you can become a sponsor. We are also actively maintaining a roadmap so you can see what are our plans for the future. The most concrete plans are some new measurement types. We are working on the HTTP measurements, which will be quite limited. Currently, our plan is to enable HTTP measurements only towards RIPE Atlas anchors. The anchors are running a simple web server with two types of files, a small file and a large file. So with all the probes, you will be able to measure the availability of the HTTP service, but we will not allow HTTP measurements towards any random target. And the plan for a bit later in the year is the wireless measurements. We are cooperating with EduRoam, and we are still in the phase of just looking at the possibility for measuring specifically authentication of EduRoam sites. So if you are from the Research and Education Network, come talk to me or my colleagues later in the breaks. These are our contact details, and I hope to hear more from you. Thank you.
Motored through that. I'm sure some of you have questions, so you've seen them, you know who they are. Be sure you actually get in touch with them over morning tea and ask your questions then, if that's okay. So once again, thank you very much to the presenters for a wonderful session. Thank you.